Welcome on this new episode of Humans of Reliability. Today we'll talk about networking, cloud reliability, and the evolving role of abstraction in infrastructure. We are joined by Marino Wijay, a SaaS solution architect at Gong, and a seasoned expert in cloud networking, Kubernetes, and service meshes. Let's jump in. Marino, can you tell us how you got started into reliability?
Yeah, reliability is such an interesting concept, and my path to reliability is not the very direct conventional path, because when I first started out in my career, I never really thought about reliability as the end game. It's actually not the end game. It's a destination when you're on a tech journey. And for me, it really was around networking, working with network technologies and seeing how different systems, different applications would connect together. And as a result of that, I began to realize, well, if all of these systems need to operate together in unison, what that would mean is you need to make sure that your network is reliable. So way back when I started off my career in the systems world, I was doing a lot of help desk and systems administration. I began to enjoy working heavily with network technologies, things like plugging in devices, router switches and whatnot. And, one thing that came up as a recurring theme throughout my career was, how do you make sure that these fabrics never go down? So there are varying conditions where a switch and a router might go down. The CPU of a router might be overloaded because it's having to process too many routing requests. A switch might just get too hot because it's sitting in a server room closet that has no air circulation and whatnot. And you start to realize how much of an important part of the entire system itself that network fabric is. So reliability is really a networking thing, in my opinion. You learn networking, you learn how it works, you learn how things connect, you learn how to route different parts of an application together. And then you begin to realize that you have to build resiliency into that network by implementing special protocols, ensuring that you don't overload a system. And we could get into the nitty gritty bits of it, but think of it this way. When you think about the network, it's like not having a road there. If you don't have the road to travel on, how do you get around? And so for me, reliability really came down to this ideology of making sure that road always existed. You had redundant ways to get around that network. Like when you're in the GTA, imagine for a second that your DVP, the Don Valley Parkway, is congested. Right? It's stuck. No one's moving. Maybe people are moving, but very, very slowly. There might be an accident there, which means that no one's getting through. And now you have to think about an alternate path to get to your destination. Well, what ends up happening is half the people might get off on Bloor, then take the Bloor exit all the way down to Bloor Street, and then they'll cross all of these different side roads, and they'll basically take the local path to get to their destination. A little bit longer, but they'll still arrive downtown Toronto if they really needed to. And that concept is heavily tied to this ideology of reliability. If you have an overloaded circuit or a backed up circuit because you don't have any mechanism to control the flow of traffic, flow control, well, that's going to affect your reliability too. So then you think about, beyond networking, right? You think about how these data centers have gravitated towards cloud environments, and cloud environments really hide the network heavily. You tell it, hey, I want a network, but you don't really specify the parameters of how that network should look like. As long as you have connectivity, things just work just fine. But what really comes to mind here is the different components we have to start using to achieve different levels of reliability or availability even. So in the world of cloud, right, AWS as a cloud provider established a set of principles and guidelines by which someone should operate in the cloud. You have to assume that something could always go wrong. So you have to build your application on top of an infrastructure with that reliability mindset in place, meaning you have to build with the assumption that something will go and break and fail and fall apart. You might lose power in a data center or an availability zone, which has happened many, many times before. Not many, but has happened before, has gone down. So how do you recover from that? And that's where some higher level constructs come up, like load balancers and DNS, and the ability to set up active environments across multiple regions in your cloud provider environment. And then you start to think about, hey, maybe I don't want to use a single cloud and I want to do multi-cloud. And so that becomes a little bit complicated too. But when you start to think about how you solve that problem, it comes back to networking.
You mentioned the concept of cloud, and you started your career racking network equipment, which back then were hardware. Virtualization has moved in now for a while in the world of networking. How do you think this has impacted networking and the reliability of it?
So virtualization is an interesting concept. Way before network virtualization became a real thing, something that a lot of people adopted, virtualization was helping us take a server and being a lot more efficient with it, a physical box, so that we can pack more workloads, more applications onto it, but provide some level of isolation, some quota to CPU memory and disk, and still ensure that we were maximizing our usage and efficiency out of a server. And through that story and through that lens, we became a lot more clever and realized, well, if we can do this for compute and storage, why not do it for the network as well? Why not virtualize the network a little bit so that we can build something repeatable, we can automate it, we can not think about the underlying hardware, and we just build a network on demand, a just-in-time network. So network virtualization or software-defined networking actually paved a path for the way we even solved reliability challenges. So I'll give you an example. Back in about 2014, around the time containers and Kubernetes started to really take off, there was this company called Nicira that was developing this network virtualization technology called NSX. And what it was really doing was allowing you to build virtual networks in a data center or across data centers using network primitives, right? Using tunneling mechanisms, using encapsulation by extending your layer 2 domain, extending your subnet where you needed to. And what that really meant was I could have two data centers that were in very different geographic locations operate as one, or seemingly operate as one in a logical sense, to the point of, hey, now I can extend my network across these two data centers and make every application, every system think they're on the same network. I could trick the systems into thinking they're on the same network. And part of the reason for wanting to solve this problem was the way developers used to build their applications way back when, because they would hard code systems and IPs into their code base, and you couldn't just simply trick a system to thinking, oh, you're going to communicate with another system in a different network. You needed to make it think it was on the same network. So this concept of VXLAN came around, where you were just tunneling your traffic in layer 2 or across the layer 3 boundary and making everything seem as if it was on the same logical network, logical subnet. And that actually was a very powerful technology that, Nicira and even Cisco and Red Hat and Intel, they all collaborated on to make this a possibility, a reality even. And then you started to see cloud providers adopt this in their own way. So AWS has their VPC technology, which is specific to a region, but isn't specific to a given data center. They allow your network to span multiple environments and make connectivity so much easier. And when you make connectivity very easy, that also translates to, I can make my reliability even easier as well. Now, this notion of network virtualization started to take off well after 2014. VMware acquires Nicira, and VMware really doubles down on this NSX technology, making it available within their vSphere environment, and then even extending it out to other compute platforms. Where they are today is interesting because that is like a smaller portion of the story, but they set the precedent for how networks should be built. And then, come to 2020, maybe even before that, we see that ideology of network virtualization make its way into microservices, smaller workloads that exist in containerized systems like Kubernetes, for example. So now that you have Kubernetes in the mix, it wants to even further abstract the network. It wants you to think that there's a network there. It doesn't matter how that network's built. It doesn't matter that there's a physical fabric underneath. I just will do things to make sure that your pods will always be able to communicate. Your containers have a communication path, but I'll figure out everything else. I'll take care of the way I stand up a network namespace and the way services inside of that network namespace need to communicate amongst each other. So Kubernetes really, I wouldn't say changed the game, but made us double down on the way network virtualization worked. And it was through this concept of container networking interfaces, a CNI implementation that there are so many out there. Like, we've got Cilium, we've got Calico, we've got many. Even cloud providers have their own, like AWS has their own VPC CNI, which directly allows you to have your pods on a VPC network. But this fundamental construct is a layer by which your containers have the ability to talk to each other, but in the sense of a just-in-time network, very much like what we were solving way back in the data center. Now, there was another problem. Right? With CNI technology, you could only do so much. You can implement your network policy, you can implement that connectivity, you can control some of that routing, but the real logic lived elsewhere. Like that real magic lived further up in that OSI stack. So at that time when Kubernetes was really starting to, develop and fly, you started to see this concept of service mesh come up. Service mesh, interestingly enough, was pulling in different ideas of networking to create a distributed system of sorts to service containerized workloads, not just for Kubernetes, but for other environments too. So there were a few service meshes that really came into the light here. You've got Kuma Mesh, you've got the Istio service mesh, you've got Linkerd, all basically creating another layer of networking on top of what we saw as CNIs. But it wasn't just about creating a network. It was about the same challenges we've been always trying to solve with reliability and disaster recovery and availability. Because what a service mesh was doing for you was allowing you to abstract the network even further, as simply put. But by using things like proxies, proxies would act on your behalf, establish communications with other proxies, and create a laneway for which your microservices can communicate, not just within a cluster, but outside of clusters to other clusters. So now your level of disaster recovery and reliability have really aligned to what SREs care about. If they're really trying to achieve that, 5 nines, 6 nines of reliability, the way they would do it is not only just using DNS and load balancers, but by using a service mesh, because now you have deeper metrics and observability into what your services are doing. Now you have much more granular control of how you can have traffic cross your wire, how you can have services communicate with each other. In fact, it even enabled this pattern that API gateways, for example, were solving, where you could do like blue, greens, and canaries for services inside of your network that didn't even touch the outside world. And that became a very powerful and recurring theme even to today. Today, I've been working with some pretty huge end users that see so much value in service mesh technology because they see it as a means to solve their active-active setups, to achieve higher levels of availability for how their applications run. And it's simply because you've got this proxy, this distributed set of proxies that are controlled from a distributed control plane that says, I want to maintain desired state, much like Kubernetes does. I want this network to always look like this. I want my services to always have a pathway to communicate with each other. And all it does is it pulls from things we used to do so many years ago. If you remember how we used to build out IPsec tunnels and set up branch networks to communicate with our data center or our HQ environments, we're taking that same model, but making it so much smaller to fit that microservices or that compute environment that houses containerized workloads. And now we see service meshes have gone well beyond that. But now, while networking's been a heavy component of it, we're starting to see how other systems like observability systems tied well into networking. Right? We used to have tools like, we still do, we have tools like Ping, Traceroute, tools like TCP dump and Wireshark that really give us insights as to what our networks are doing at a lower level. But what about when we're thinking about at a higher level with applications, right? When we have applications that need to communicate with each other, when we start seeing a bunch of HTTP 500 status codes or 400 status codes, how do we work around those? How do we solve for that? How do we understand when there's a service in a service path that has been overloaded and we need to find a way to recover from it or make it much more reliable of sorts? So we've seen networking transform alongside reliability just to be able to accommodate for those reliability needs.
So we spoke a lot about layer of abstraction, and I think the convergence is going to making sure that applications are scalable and reliable, and that's the main goal of Kubernetes. And now for decades, we've been optimizing for web applications where response time was really important. We are trying to shave off milliseconds. Now there is a shift with AI workload. One of the interesting differences is that oftentimes, a longer request to a model means a better result. So we are not always optimizing for speed. So speaking of transformation, have you seen, and we're still early in this boom of AI, but have you seen a transformation happening when it comes to networking and reliability with this boom of AI workloads?
Yes and no. So there's transformation in the sense that we're adapting to the way we want to communicate and work with AI technologies or LLMs. I mean, at the end of the day, all LLMs offer up an API by which we can communicate with. I mean, ChatGPT or Mistral or Cloud, they're all front ends for some back-end LLMs. And we communicate through this API to be able to transact. We'll pass in information through a request, which is decorated in so many ways. It's prettified, if you want to think of it that way, so that when it reaches that LLM, it's deconstructed. The LLM is reading it, understanding what you want, and then sending you the output that you desire. To your point, right? We want LLMs to take their time, to be thoughtful, to take the context that we've given that LLM or that model to give us a much more accurate, much more specific answer. And there's a lot of ways to solve for that problem, right? Networking can slow things down and speed things up. Let's take the API gateway for a second, because everything is an API today. Now, if we are transacting with multiple LLMs today, and maybe we have some requirements within the enterprise where maybe I want to save some cost, but I also want to be highly accurate. Maybe I can host local LLMs that are low cost and can definitely respond quicker to very basic tasks and requests. But for the more heavier requests, the ones that require more thinking, more reasoning, more thought, well, maybe we can send them up to a cloud provider, a non-hosted model if we wanted to, because we also want to be able to find the right balance of cost versus performance. And so I use maybe an AI proxy, which is an API gateway of sorts, but I implement that same kind of logic, whether it's a service mesh or an API gateway, I implement that same kind of logic. And based off of certain conditions, I'll send my request to OpenAI and its API. Under other conditions, I'll send my traffic locally to a local LLM, like Olama, for example, or even DeepSeek. Now, what are those conditions? Could be availability, could be reliability, right? Okay, my local LLM is down for maintenance at the moment because we're doing some upgrades. For the interim, for that short period of time, that maintenance window, let's send all the requests to Anthropic and get some good, solid responses. Or there might be a situation where there are multiple teams that are working together. Some of them might be sending the same queries up to these LLMs. Why not cache? Why not store this in a cache somewhere so that when our queries come through, our AI proxy intercepts, sees that request, and can just return a very similar response because it evaluates that query or that prompt, realizes, wait, this is the exact same thing that you just asked me like maybe 5 minutes ago. I'm going to return a response, and that will speed up how quickly you get a response. But not only that, it cuts back on your cost because now you're not having to send your request up to a model, consume your credits. You're actually using an already asked questions response that's been stored in like a Redis environment of sorts, like a vector DB. Now, this is actually pretty powerful, but then you start to extend that capability to other areas too. Like, hold on a second, I'm using network primitives to even help me make sure I don't ask harmful prompts or queries. I'm sanitizing my requests as they make it to the LLM. I might be trying to optimize my day job by feeding in a bunch of data and saying, look, take this data and, calculate some output for me, give me that response. But what I don't want to do is send PII, personally identifiable information. I don't want to send my SIN number up there to the LLM. I don't want to send my credit card information. Sanitize that before you send it up and then return a response. And sometimes models aren't able to discern that, but a proxy will be able to, because it'll intercept that. It'll look at your request, and then it'll see, okay, wait, there's something in this request altogether we need to remove or redact, and then we can send it for processing and then return. We can transform that if we want to. So there's a lot of power that networking primitives from way back, in the API gateway and service mesh days can solve for with respect to AI and consuming AI. So that's the yes side of it. Like the no side of it is an AI technology is advancing in so many different ways too, that sometimes even these systems themselves have their own mechanism to do that proxying as well, like caching or even being able to shift between models. Let's just say you want to use 4.0 versus 4.5. 4.5 is a little bit more expensive. Even 0.1 is a little bit more expensive than 4.5 because it provides more reasoning. But sometimes you want to use 0.1 because you need that reasoning. You need it to think a little bit deeply about how it returns that request to you. It can't just be a standard off-the-shelf response. It has to be very thought out. I'm looking for a way to integrate Rootly with Slack and Teams and some other systems out there. Give me a set of instructions. Sure, 4.0 and 4.5 can go source that information off the internet, but 0.1 will take some time to think about that. But all of that is just networking behind the scenes that we don't see.
So we spoke a lot about different layers of abstraction, virtualization. At the end of the day, it's all controlled by humans. So how do you think what role they play in all this reliability scheme?
Humans play a critical role with reliability because they provide a lot of context, but they also bring a lot of empathy. Empathy not towards the application, but towards the people that work with these other technologies, work with the output, work with consuming these systems, work with end users. And that's something that can never be replaced, right? Humans bring the element of, I need to give it enough logic, but also I need to handhold this system to make sure that we get to that destination and get a proper response. Humans are the ones that have built these systems to make it easier, more convenient for us to consume, but humans are the ones that are also consuming. So we have to be thoughtful. We have to be mindful about the way we train our systems. We train these models. We have to be mindful of being inclusive, to think about ways that we don't harm others, right? We don't provide output that could be malicious code, for example. Maybe we are providing that context of don't just go scrape GitHub for a response because we might actually be violating a whole bunch of copyright laws or violating a lot of those licenses that are up there for a reason. Be thoughtful about that. Look for a certain type of license that allows us to reuse some of this information, but also take that information and help us modify it. And this is all humans. We think about this stuff. If you think about it, we could have had AI avatars do this entire podcast or webinar for us if we wanted to, right? But then it wouldn't come from the heart. And that's the other part of it too. Humans give a lot of heart when they do something. we think and reason well beyond what a model can do. And, O1 is very intelligent. O3 Mini, a lot of the other models out there, even DeepSeek R1, they're very good at reasoning, but they're not good at combining that reasoning with empathy and heart. And that's where we come in. We're there to really think about the implications of how AI can be damaging, but also be very helpful and convenient. And without us, quite honestly, there wouldn't actually be real working usage of AI. I mean, in fact, AI would be useless without us.
Former guest on the podcast said that LLMs don't have skin in the game and you should not trust them. So I think there is a bridge between this and what you just shared. Marino, if people want to find you on the internet, where should they go?
They absolutely can just search me up on any search engine that they want by my name, but I am also on the X platform. I'm on LinkedIn. I'm on Blue Sky. I've got a YouTube channel where I stream weekly as much as I possibly can just to dig into technologies, but not at I'm going to code all stream long. We spend some time to really talk about the ideas and the methods and even the motivations for what we're trying to build and why we build it. For example, Ned and I are building out an AI agent to help us transcribe some of our shows, some of our audios that we've developed and create actionable output so that it can help us in our day jobs and optimize our day jobs as well, but also even on our daily lives as well. And it's things like that where we want to be intentional. So you could always find me in any one of these platforms. I'm always around. I'm hanging around on the internet quite often. So it won't be hard to find me.
Super. Marino, thank you for coming.
Thank you. Thank you, Sylvain. I appreciate you having me here.